So now that we have our statements, which we talked about in section 2.1, we want to be able to connect statements together to build new statements. And we can do that with these logic connectives and, or, and not. So these, mean very similar to what we use them in English to mean, although we'll see there's a couple things we have to be careful of. Let's go over just basic symbols and meanings here. So the symbol for and is this upward facing wedge here. So if you're trying to type that in LaTeX, it is wedge. And it means that both statements must be true. Right? So I'm only going to get P and Q. This is going to be true when P is true and also Q is true, right? So I'm actually defining the word and with the word and in there, so it's obviously not the best definition, but I think we can kind of get that meaning. For or, I'm going to use this guy, so its command in LaTeX is V, because it just kind of looks like a V, and that meaning is that one or the other is true, or both. Right, so if you sort of think about it in the right way, this is kind of like the intersection. Right, it's only going to work if it works for both of them. And this one's kind of like the union. As long as it's one is true or the other is true, as long as you're in one set or in the other set, then it's going to be true. Right, so P or Q is true when either P is true or Q is true. So again, I'm using the word or here to define my or, but that is the English sort of meaning that we're used to here. Okay, and then not. The symbol that we're going to use in this book is this little tilde symbol. So you can get to that by typing /sim. You'll also sometimes see this symbol used for not. And if you want to LaTeX that, that's /neg, N-E-G. Not to be confused with NAQ, which is not equal to. Okay, so that means basically the opposite truth value. So if I have negate something that's true, then it's false. And if I negate something that's false, then it's true. So not P is true when P is false. And vice versa, not P is false when P is true. So it's just going to negate that truth value. So let's do some examples with these logic connectives. I've got 3 statements written up here. 2 is even is the statement P. 3 is an R is the statement Q. And 3 plus 2 equals 7 is the statement R. So first let's go through and determine if each of those statements are true or false. 2 is even. Sounds pretty good. That's true. So I'm going to use capital T for true here. Q, 3 is an R. Yep, 3 is a real number. That's good. And then R, 3 plus 2 is 7. That is not right. So that is false. Okay, so now let's practice using our logic connectives. So I've got P and Q. So is it true that 2 is even and 3 is a real number? Yes, right? So this is going to be true and true. Ooh, and true is true. I said yes, but I wrote F. Let's fix that. Much better. So true and true is true. Is it true that 2 is even and 3 plus 2 equals 7? No, that's not true, right? 2 was even, but that had to be true along with 3 plus 2 being 7. And if I have an and here with a false, I don't get a true. I get a false there. P or Q, right? This is P is true, Q is true. So true or true, that's going to be true. P or R, so that's saying that 2 is even, or 3 plus 2 is 7. That's okay, right? That's going to be a true or a false. And as long as at least one of those is true, we get true. Not Q, it is not the case that 3 is an R. That's false. Sorry, again, I wrote the wrong thing. That's false, because I have a not true. And finally, we have a P and not R. So P was true, and not R was false. So that's the same as true and true, and we know that true and true is true. So it is true that 2 is even, and 3 plus 2 is not 7. That's another way we can think about that. So sometimes when we're thinking about these logic connectives, it's helpful to go through and actually think about all possible cases for P and Q, and whether or not those statements will be true and false. So P has two options. It can either be true or it could be false. Q has two options. It can either be true or it can be false. So I know that there's 2 times 2 is 4 total options here. So the easiest way to do it, I'm going to sort of list them in this alphabetical-like order, I guess reverse alphabetical. So I'll do my 2 trues and then my true falses, 2 falses, and then I will alternate true, false. And so I got all possible combinations there. Now, remember this first guy here is and, so that's only true if they're both true. Otherwise, it's going to be false. Next, we have our or. So that's true as long as one or the other or both are true, but it will be false if they're both false. And then not P is false when P is true, and true when P is false. So using this, we can kind of remember exactly what all these symbols are doing. So take some time and really think about this truth table and make sure you'd be able to reproduce this. For practice, I'd like you to go through and find statements P, and maybe you need extra statements Q and R, so you can rewrite these 3 statements below using the and, the or, and the not. So we have the statement, the number 2 is both even and a power of 2. So I want you to rewrite that with that and connective. The matrix A is not invertible, so that one should have a not in it. And finally, I run every day unless it rains. So see if you can think of a way to rewrite that using and, ors, and nots. When we're comparing math and our typical English use of these words, we have to be a little bit careful because they're not always used the same way. So let's consider this first statement here. It says your dinner comes with either soup or salad, right? If you're at a restaurant and someone says, do you want soup or salad? You can't just say both. Right? That's not allowed. So usually in English, we think of this or as an exclusive or. Right? We don't allow both. In math, we always allow both. So we just have to be a little bit careful about that. If you ever say or in math, then in the case where both things are true, that statement is still true. So if someone says, every person eats soup or salad for dinner, and you had both soup and salad, you wouldn't be breaking that statement. You wouldn't be negating that or being a counterexample to that. Right, and we do sometimes use or in English that way, right? If somebody said everyone likes plain or pepperoni pizza, we wouldn't exclude necessarily people who like both. So, right, sometimes we're using the exclusive or in English and sometimes we're not, but in math, we're always going to allow both to be a possibility. We also have to be a little bit careful about negating sentences or statements here. So let's say I have the statement, the number 4 is even, and I want to negate that, right? There's lots of different ways I could do it. I could say the number 4 is not even. I could say, sort of really boring or really direct, it is not the case that the number 4 is even. Right? If you're doing sort of the lazy way to negate statements, you can often just put the words, it is not the case that, in front of them. But that's not usually the English way that we would negate it. Perhaps I could say the number 4 is odd, right? But that might not actually be the right negation, because if I'm saying that either a number is even or I'm saying it's odd, we're not considering non-integers, right? So what about half, right? It's not either even or odd, or e or pi. So this is kind of this question of whatever your universe is. It's the issue we had with complements as well. So we have to be a little bit careful about that when we're negating. So keep that in mind when we're thinking about this. We sort of need this overarching theme to know how I should negate. Okay, so to finish up, there's a couple more things for you to think about negating here. So I've got two statements. The first one says, everyone here has 2 sisters. And the second one says, the function f is continuous and increasing. So I want you to think about the negation of each of those 2 sentences, or those 2 statements. And we'll talk about that in class.